Welcome. 2 days ago, on March 3rd, 2018, Gus and I conducted a SIG, which stands for a Special Interest Group, at the meeting of the American Glaucoma Society that was held in New York City. And before I present some of the material we presented at that meeting, the obligatory financial disclosures can be found at the bottom of this slide. Before I start, in terms of background, you could read a general summary of our position in this perspective that was published in February 2018 in IOVS. Or you can go to these two Progress Retinal Eye Research review papers that were published in 2017 and 2013. The most recent one is most closely related to the general gist. The second 2013 paper covers the more specific issue of damage to the macula. And then you already know there are other lectures that can be found on this website. All right, so the question we posed was, are we in the middle of a paradigm shift? So what do we mean by a paradigm shift? So we're going to define a common clinical paradigm for detecting glaucoma as the following 3 tests. The first is some kind of an examination of the disc, physical exam, often augmented with a fundus photo, with a photo of some kind. For a visual field, it is traditional to do a 24-2, although in some places they might do a 30-2. In either case, we're talking about a 6-degree grid. And then for an OCT, in this common clinical paradigm that we're defining, only the disc is scanned, typically in this day and age with a cube scan, and summarized in a report like the one you see here. Now, when we first started lecturing on macular damage and the need to change the clinical paradigm, I think it's fair to say that this was about 2012 or so. I think it's fair to say that at that point, nearly all clinicians diagnosed glaucoma based upon these 3 exams. Some of that's changing, although even today, I think the overwhelming majority still use this common clinical paradigm. The common clinical paradigm also includes a heavy reliance on metrics. So it's particularly true for the OCT scan, where the average nerve fiber thickness is the common metric, along perhaps with the thickness of the quadrants. Less so for the visual fields, although glaucoma hemifield test and pan-standard deviations are heavily dependent upon, as well as mean deviation. But in the case of the visual fields, I think most clinicians will look at the pattern of defect, and many clinicians also will look at this plot over here on the OCT. Okay, so the purpose of the SIG and the purpose of these lectures is to discuss the extent to which this paradigm is or should be changing. And I'm going to present 3 mini lectures, in a sense, on the 3 challenges to the common clinical paradigm. The first is that early glaucomatous damage includes the macula and is very common. The second, which we'll do in detail later in the lecture, says that typically structure and function agree, but you can't use metrics, or you shouldn't use metrics to assess this agreement. And then the third has to do with the details that can be seen on OCT. So let's just take the first. Early glaucomatous damage includes the macula and is very common. So what do we mean by macula? Because different specialties define macula differently. For us, it's going to mean plus or minus 8 degrees. So on a fundus picture here, here's a circle with a radius of 8 degrees. In this region, which represents less than 2% of the retinal area, in this region, more than 30% of your retinal ganglion cells can be found. And as you know, this region is so vital for reading, driving, face recognition, and so on. Here's a thickness plot of the retinal ganglion cell plus interplexiform layer from an OCT cube scan. So here's one of the B scans. This went through the fovea. Here is a blow-up or illustration of that region. And what we're showing in pseudo color here is the thickness of the retinal ganglion cell plus inner plexiform layer here. So there's the fovea, so there's no retinal ganglion cell layer there. So dark blue here is very thin, dark red is very thick, and it's very thick in part because ganglion cells are being pushed away from the fovea, and in part because you just have more ganglion cells in the macula. So why does early glaucomatous damage include the macula? This was a question that was first posed to us about 8 years ago by our colleague Bob Rich, and he wanted to know, why does he see so many patients with what he called a comet defect near fixation? All right, so to answer that question, let's go back and review where on the disc we think the most retinal nerve fiber layer damage occurs. So it's commonly accepted that the superior quadrant here and inferior quadrant are particularly vulnerable to damage from glaucoma. And there's a lot of OCT data on this now. The histological data comes from a series of nice studies by Harry Quigley and colleagues. So here's some data we collected and presented in 2013 that's relevant. So let's look at retinal nerve fiber layer thickness first. So here's retinal nerve fiber layer thickness from a cube scan of the disc. And this is average of 54 healthy controls over 40. Blue is thinner, red is thicker, so that's healthy. So here are patients with moderate glaucoma. Mean deviations worse than -6 to, 10 or 12. And you can see missing retinal nerve fiber layer. So what we're going to do here is take this and subtract this from this. So now red means something different. Red is going to be a lot of thinning. So green is not thinner than normal. Red is much thinner than normal. So let's blow this up. And again, extensive thinning here within normal limits. Now notice that it's the temporal half of the superior and inferior quadrants that are most vulnerable. So it's this region here where most thinning has occurred, as opposed to there, and here as opposed to over here. So let's take this and move it over here. So that's vulnerable, and there's the thinning map. So we've called this in a recent paper the superior vulnerability zone and inferior vulnerability zone, just to give it a name. All right, so that's what's happening at the disc and happening to retinal nerve fiber layer. Now, what's happening in the macula and to retinal ganglion cell damage? Well, let's replace this with a retinal ganglion cell thickness map of the macula. There it is for the healthy controls. There it is for the same patients. Here's the difference. Again, we're subtracting this from this. And here's your difference map, extensive thinning within normal limits. So let's move that over here. So this is retinal ganglion cell loss. This is retinal nerve fiber layer loss. All right, based on work we have done and others have done, we've developed a schematic model of the macula, and you can see it here superimposed on bundle tracings from Jansonius et al. So what this is meant to capture is this region here of the macula is sending its axons, or the ganglion cells are sending their axons, to this region of the disc. So what I want you to notice is the inferior part of the macula sends its axons not to the temporal half, but right smack into the most vulnerable region of the eye. Over here, these axons go right smack into the inferior vulnerability zone. We can blow this up here, plus or minus 8 degrees, most damage. This region here sends its axons into the temporal quadrant and is less vulnerable to damage. This region here sends its axons into the inferior vulnerability zone and is more vulnerable to damage. And we call this region of the disc the macular vulnerability zone. All right, so why does early damage include the macula? Well, there are really two reasons. A major reason here is that you see local defects because the damage to the macular vulnerability zone is very, very common. There's also a second reason. Glaucoma has an overall diffuse or widespread damage that we and others have documented, and that also affects the macula. All right, so where do we look for location of the macula on the circumpapillary retinal nerve fibrillary plot? So here is a circumpapillary thickness plot that you're used to. This is often called a T-SNP plot because it's plotted the way the original scans were done, starting here in the center of the temporal and then going counterclockwise. So temporal, superior, inferior, nasal, inferior, temporal, T-SNP. On this plot, the macula is split. So this would be the upper macula, this would, which is partially over here as well, by the way, and this is the inferior macula, superior macula, inferior macula. All right. Here's your superior vulnerability zones, your inferior vulnerability zones, and this is where you would locate your macular vulnerability zone. All right, here's the T-SNP plot that we recommend. We've been arguing for years that this is really silly to plot it this way. You really want to plot it so that your macula is in the center of your of this. It makes it much easier to compare to visual fields. So now we're plotting it as if it was scanned starting in the center of the nasal disc and going counterclockwise. And if we will present this later, but our complete model here argues that for the temporal half of the disc, you are getting input from plus or minus 15 degrees plus the nasal step. Okay, so, and it is very common. So there's a lot of evidence now accumulating about how common it is, although for those of you who are skeptics, take this as a working hypothesis and go out and test it. We're arguing that early glaucoma damage includes the macula and is very common. So here's one piece of evidence. So in this study here, which I'll tell you more about later, we had 57 eyes with early glaucoma. By early glaucoma, I'm going to mean nothing more than the 24-2 mean deviation was better than -6. So 2 glaucoma specialists had, who were not involved in the care of the patient, had all the information we had on the patient. They had OCT, they had 24-2 and 10-2 visual fields, in many cases repeat studies, stereo photos, IOP, history, etc. And they judged that 57 of these had glaucoma. We then took the 57 in a more recent study, and we asked, well, let's first take the superior vulnerability zone, which is right here. This is now an end-stent plot. So let's take this. Is this eye thin there? And we're going to use thinning, meaning dipping into the red. Well, no, it's not. All right. Well, what about inferior vulnerability zone? Well, that's over here. Yes, it is affected. What about macular vulnerability zone? Oops, sorry. Again, yes, it's affected. And when we finished this, we found that 55 out of 57 eyes had damage in either the superior vulnerability zone and or the inferior vulnerability zone. You notice that 80% had damage in here. And in fact, even these other 2 eyes, qualitatively, you would say they were damaged. They were in the yellow region of the OCT. So essentially all the eyes that we looked at had damage in these 2 zones. Again, a testable hypothesis. So the macular vulnerability zone, in fact, 3/4 of these eyes had damage there. Overall, the macula 87%. So damage to the macula was common, and damage to the macular vulnerability zone was common. In this case, about 3/4. Now, we're replicating this. Others have or are replicating this. It's going to depend on your sample size. If you have more normal tension than some other sample, you're going to have more macular vulnerability zone. If you have more hypertensives, you might have some less. But in any case, we're arguing, and it's testable, that it's very common. All right, this causes two problems for the common clinical paradigm. And they cause, first of all, the first problem, I should say, occurs because the 24-2 points poorly sample the macular region. So here are the locations of those points plotted against where they would where the ganglion cell location that they would be testing. And I want you to notice that only the central 4 points fall within the macula, and they sample this damage very poorly. So remember, this is extensive thinning, and here are 4 points. Right? A number of studies now have documented that the 24-2 and 30-2, that is the 6-degree grid, can miss or underestimate macular damage. And here are some publications. Solution to this: you want to obtain 10-2 visual fields or use a modified 24-2 pattern. We'll say more about this later. All right, so here's an example. Here's an eye where 24-2 and 10-2 is obtained on the same day. Clear damage here, nice deep defect. You're missing it on the 24-2. Okay, a second problem that the common clinical paradigm creates is that the OCT analysis of disc scans can miss macular damage. So here's an eye, that you can see this is normal. Global thickness would be normal. Even the clock hours are normal. See that? That's real damage. So here it is on another plot, different kind of plot. And it's right in the macula. This is an instant plot. And that's because the damage is right about here. Okay, the solution to this is obtain a scan of the macula as well as the disc. You want a scan of the macula. So I'm going to show you for this eye a cube scan of the macula, and in this case there were 128 B scans. Here's what one of them looks like. This is the thickness plot for healthy eyes. This is what it looks like for this patient. You can see looks like somebody took a bite out of it. So the damage is often easier to see on probability deviation maps. So many machines will take this and turn this into a probability map. And the way you read this is continuous probability. Green means better than 10%. Dark red is 0.1%. Red would be 1%. Yellow would be 5%. That defect there is this right here. Okay, so early glaucomatous damage includes the macula and is very common. And recommendation here is you want to include a visual field with a finer grid, a 10-2, or a modified 24-2, which is actually becoming available for the Humphrey machine. And the OCT must, I would argue, include cube scans not only of the disc but also the macula, or a single cube scan if it includes both the macula and the disc. Are there such plots on my instrument, you may add? And at the very end of this series of lectures, I will address that question. Okay, at this point there was a discussion at the SIG meeting. Here, I'll just pause for a moment and then we'll pick up the second challenge. So the second challenge we discussed had to do with structural and functional damage. And we're going to argue that they typically agree, but visual fields and OCT metrics are a poor way to assess disagreement. And again, you can take this as a working hypothesis issue if you want, and test this yourself with your own data. So there are 2 points here. Let's start with the second point, that visual field and OCT metrics are a poor way to assess disagreement. So let's return to the study I already mentioned. There actually were 102 eyes. In addition to the 57 eyes judged glaucomatous by our specialists, 45 were judged to be healthy suspects. Suspects because many of them had abnormal discs, or at least funny-looking discs, tilted or whatever. The 24-2 mistakes, and again I put mistakes in quotes because we don't have a gold standard, it's a reference standard, but that is the false positives plus the false negatives out of 102 based on our reference standard. Range from 30 to 20. Let's just take this here. This is a commonly used metric where you consider an eye abnormal if the pattern standard deviation or glaucoma hemifield test was abnormal, right? The disc scan metrics did better, but even here there were 13 mistakes if you used quadrants, 15 if you used a more typical global average. OCT, or visual field metrics, are a poor way to detect early damage. So what should we expect visual fields in OCT to agree? Should we expect, I should say, visual fields in OCT to agree? Well, it's often said structural damage precedes functional damage, so the current wisdom would say no. All right, and let's just look at a plot like this. I'd say I saw this plot at least 6 times at the American Glaucoma Society in 2018, in each case making this point here. So what is this plot meant to show? Well, this is relative loss, sensitivity, let's say, or retinal nerve fiber layer thinning, and this is over time, and it's meant to capture the belief that, and in some cases data, depending on the metric used, that while visual field function may not be changing, structure is changing. This is a gross oversimplification. And if you want to hear the details of the argument, you can read a review that Randy Carden and I wrote in 2007, or a review by Malik, Bill Swanson, and Ted Gower-Heath. In practice, whether damage is seen or detected first on structural or functional tests are going to depend on at least 3 factors. First, the test used. You're going to get very different results in early glaucoma if you use a 24-2 or a 10-2 or a combination, for example. You're also going to get poor agreement if you use metrics. And finally, the agreement that you get is going to depend upon the baseline conditions you start with. Now, this is a little complicated, but let me try to explain it, and then we'll return to it later. Suppose you started out life with a relatively thick, compared to the average, but still within normal range, OCT, retinal nerve fiber layer, but a relatively poor visual sensitivity, but again in the normal range. And I started out life, for whatever reason, with a very good visual sensitivity. I mean, I'm an experienced psychophysical observer, for example, right? But a relatively poor OCT thickness, but again within normal range. Suppose we both get glaucoma. It's going to show up first on me for the OCT, because I started out with a relatively thin retinal nerve fiber layer, and first on you for the visual field, because you started out with a relatively low visual field sensitivity. We'll return to this. Should we expect it to agree? Fields to agree with OCT? The answer is yes in most, maybe nearly all cases, if you have reliable and repeatable visual fields and/or repeatable visual fields, but not if you only use a 24 or 30-2 test pattern. In some cases, you need a 10-2 test pattern. Or if you only look at pattern deviation plots and ignore total deviation plots, in many cases, total deviation plot is more accurate. And not if you use typical metrics. So yes, in nearly all cases, but only if you topographically compare the abnormal regions on the 24-2 and 10-2 to those on the OCT retinal ganglion cell and/or retinal nerve fiber layer probability plots. So here's a report from one of the machines. I'll explain in the separate lecture that's part of this group of lectures what's plotted here and how you can find similar information on other machines. But for now, I want you to notice this probability plot. It's the probability plot based on this thickness plot down here, right? Dark red means abnormal, green means normal range. And it's in field view, that is, it's been flipped along the midline to compare with visual field. The large points here are the locations of the 24-2 visual field points. The small points are the location for the 10-2. Same thing. 24-2 points, 10-2 points. All right, now this is what we can do. Here's the visual field for this patient. We can circle an abnormal region, circle it here, circle this abnormal region, circle it there, and you can see how these arcuates here are agreeing with the visual field. Same thing with the 10-2, we can circle this and put it over here, circle it there, put it over here, right? So we actually tried to do this more quantitatively in a paper we're going to be presenting at ARVO. We had the same 102 eyes I've been telling you about, and we used a set of criteria that that required the abnormal points here to overlap the abnormal points or the red region on the OCT. And what we found was excellent agreement was obtained between damage seen on the visual field in the OCT as long as you use this topographical method. If you use the conventional metrics, it was not good. So here was the conventional metrics for these eyes. When we did our comparison, there were only 3 so-called mistakes. All right, in most cases, the agreement between structure and function based on abnormal points is very, very good. In most eyes, nearly all eyes, if you have reliable fields, okay? However, it is true that sometimes structural damage on OCT will appear more obvious than functional damage. That is true. And here's an eye with so-called preparametric damage, although I'll argue in a moment, preparametric damage is very rare. Nothing here. But look over here where I just added this, right? This defect here is falling between the 24-2 points. If we put it over here, it would fall between the points. And that's why this is normal. Normal, normal. You can actually see the defect in this case. There's the defect on the image. And I'll say more later about why you want to look at these images. Okay, so let's look at the retinal ganglion cell plot. It has this abnormal region here. It looks like it corresponds to this. Let's circle this, and we circle that. It agrees. We circle this, and we circle that. It agrees. So that's abnormal, and it agrees with that. All right, so total deviation often provides more accurate picture than the pattern standard deviation. So here's an example. You know, this eye glaucoma heavy field test was borderline. Pattern deviation totally normal. Mean deviation down. You can see why here. This is totally, essentially normal. You know, this is clearly abnormal. If you believe this, you would never expect all of the damage you can see on the OCT. And on the other hand, the total deviation does agree well with the abnormal regions on the OCT. It's even possible to see functional, that is visual field damage, that's more obvious than structural, although this is less often the case than the reverse. So let's blow this up here, and you can see the mean deviation is abnormal, pattern standard deviation is abnormal. I'd say this is clear arcuate damage, certainly here. Let's circle those points. This looks also to be relatively clear, maybe not as clear as that. Visual field's clearly abnormal, yes? Global thickness here, normal range. Quadrants, normal range, including the inferior quadrant, which corresponds to this, and the superior quadrant, which corresponds to this. You see one yellow, but if you believe this in general, if that was your rule, you would have a lot of false positives because there are many healthy controls that have one yellow. Okay, if we superimpose this now on here and superimpose this here, that you can see this, the agreement. Now, for me at least, this is much more obvious than this, especially when you consider that vessel placement can sometimes give you artifacts that look like this. But in this case, this is real. And this here corresponds to that. I'm sorry, this here corresponds to that. And the thinning here would be associated with this over here. Okay, so why in this case? You know, this is a case, something like I was referring to that for you. I think in this particular case, this eye started out much thicker. We actually have evidence for that in here because here's the other eye. Let's take this and superimpose it. Right? This eye undoubtedly started out up here someplace, and all of this had to be lost before you started seeing this damage, whereas the visual field started showing it much earlier. Okay, so actual preparametric eyes are relatively rare if you get both 24 and 10-2 points. So here's one that looked preparametric. In fact, it's the only one we had out of that 102 that looked preparametric on both 10-2 and 24-2. So here's a 24-2, normal, normal, normal. Here's a 10-2, also normal. That was clean. That looks clean. There's something going on here. I believe it's real because you can see it here and you can see it down here. That point probably is real, but you would never believe it based on only this evidence. You can see the damage up here too as well on this photo. Right? Here it is down here on the thickness map. Now, preparametric, well, maybe we should have done a second test then. Certainly, 8 months later, when we do the test, we now have a normal set of metrics, but a clear nasal step. So let's blow that up, circle the nasal step. There it is right there. So this damage here, right, is real. It corresponds to this location. So you might say, what's the big deal? So this was, you missed a very early nasal step, but that's okay. It's not near fixation. Well, not true. So here's the thinning. Here's the retinal nerve fiber layer thickness. And the dotted curve here is 2013. 4 years later, it's clearly progressed, and now it's in the macula. Right? You can see this progression was in the macular region. So although you have just discovered an early nasal step, in fact, what you were missing all along was progressive macular damage, because this is also abnormal in this region here. All right, so in terms of the implications for the common clinical paradigm, we're arguing you want to pay attention to both pattern deviation and total deviation probability maps, not the metrics. And in terms of structure and function, you want to compare abnormal regions on the ganglion cell and retinal nerve fiber maps to abnormal points on the 24-2 and 10-2. And in the separate module, I'll address the question, can I compare abnormal regions on my OCT scans? At this point at the SIG, we had a discussion section. I'll pause for a moment and then proceed to challenge number 3. Okay, challenge number 3. Details on glaucomatous damage can be seen on OCT scans. So what do we mean by this? Well, here's the original time domain Zeiss report that most of us used if we were using OCT 10 years ago. And here's what the image looks like. You know, it's very small here. You can see why it's small. If you saw the quality of this image, you wouldn't believe that this report and that machine did as well as it did. And it did do well, right? However, with the advent of spectral domain and now swept source domain, the images are much better. And now, when I say now, this image was obtained 8 years ago on a spectral domain machine. So we've had images of this quality for at least 8 years on conventional machines that you use. Right? The detail is incredible. These little hyper-reflective regions are preserved retinal nerve fiber bundles. Now, we didn't believe that, so I don't expect you to believe that. And right there. So we did this study a couple of years ago in which we used an AOSLO machine, state-of-the-art, built by Professor Alf Duber, and with the collaboration of Richard Rosen, who owned the machine, and Toko Chu, who was the expert in running and interpreting these images, we did the following study. We compared AOSLO, so here's a series of images. It took about 45 minutes for Toko to obtain these. And we compared it to the swept source, not swept source, the spectral domain OCT. And here's the OCT scan now. And again, this kind of quality has been around for 8 years. And what I want you to notice, well, first of all, this took, as I said, 45 minutes. This took about a second and a half and then a few seconds to analyze. All right, now I want you to notice that these are abnormal regions with abnormal reflective bundles of retinal nerve fiber layer. And you can see where you have abnormal bundles, you have highly reflective retinal nerve fiber layer. Where the bundles are missing, there's almost nothing here. Bundles, you see something. Missing, almost nothing, and so on. All right? So you can see regions of preserved retinal nerve fiber bundles on OCT. That's the kind of detail that's been available. There's so much more information available in OCT scans than available in summary metrics and/or typical glaucoma reports. And the common clinical paradigm ignores these details because in most cases, glaucoma specialists aren't even looking at the images. Okay, why would you inspect the actual images? Well, I can give you 3 reasons. The first and least important but practical is you want to assess the quality of the scan. I never look at the quality scores, ever. Instead, I look at the scan to see the quality. And in some cases, you're going to see algorithm failures because all computer segment algorithms make mistakes. So over here, you've got a common mistake in which because the contrast is low, the algorithm is picking up retinal ganglion cell as well as other layers and combining it into retinal nerve fiber layer. I mean, here you're missing some tissue because it's next to a vessel. Here you've got an epiretinal membrane that's confusing the algorithm, and here a vitreal separation. So you want to carefully examine the circumpapillary scans for scanning and segmentation errors. Much more important, by looking at the scan, you can actually study eyes with advanced glaucoma and also high myopia. And, now, if you want to hear about high myopia, take a look at the modules that are on my website from the lectures I gave at SUNY, because I'm going to focus here on advanced glaucoma. So the common wisdom is you cannot use OCT to follow advanced glaucoma. That's just not true. You can use it, but you have to ignore metrics such as global and quadrant retinal nerve fiber layer thickness. You have to look at, for example, a circle scan image as well as the retinal ganglion cell and retinal nerve fiber layer plots or maps. So here's a study by Medeiros et al. I'm not picking on them. I'm actually choosing this because I think it's a really pretty study. Ted Gower-Heath and his group and my group and my colleagues and I have published similar data, and this study and our studies have been used to argue that you can't use OCT to follow advanced glaucoma. So again, I like this study because there are a lot of data points. It was really well done. And it's plotted on the y-axis here. Each dot's an eye. For that eye, this is the mean deviation on the 24-2, and this is the average thickness on the OCT. I'm just more used to flipping it, so I'm going to flip it here so that the axis now, this is now retinal nerve fiber layer. So again, this is average or global retinal nerve fiber layer. So this would be thick, this would be thin. Notice it doesn't go to 0, so 0 is down here someplace. Right? And this is mean deviation. This would be good visual field, so that's 0 dB, so that's the same as the mean for the age-matched group. And this is poor visual field. What Medeiros et al. Found and what Ted and we found was that once you get beyond 15 dB, actually once you get beyond about 10 dB, then these values tend to be asymptotic. That is, on average, the mean deviation, the global thickness is not decreasing significantly as visual field gets worse. That line was the mean. All right, so we have a study. We're going to present at ARVO, where we now have a few more extra eyes. But for the first 49 here, this was the range of mean deviations. So we were in this range here. And this was the range of global thickness. So we're in this range here. So all our eyes are in this range right about like that. All right, so here's an example. Here's an eye with the global thickness is 32 microns. Visual field, mean deviation, almost minus 25. So on this kind of a plot, it would be way down here someplace. So minus 25 and about 32. But notice there's preserved vision here. Thus the argument you can use the visual field, and you can see it here on the 10-2. Okay, here's the rule. And again, you can take this if you want as a hypothesis to be tested against your own data. But our hypothesis, and the hypothesis for which we have evidence for, is if there's a region of preserved visual fields, then there'll be a region of circumpapillary retinal nerve fibrillary remaining. And now by preserved visual field, I want to be precise, I mean a region better than -10, -8, that range of dB. So if you've got some region over here someplace, not global, but some local little point or two over here, you're going to see preserved retinal nerve fibrillary thickness. And let's use this eye as an example. So let's blow this up here. So this is now end-stin. So here's your macular region. Here's your visual field, right? Here's your ±8 degrees. Here's the model, a model of the macula. So this edge here would correspond to about there, and that edge to about there, right? So even though this point's here, all of this preserved vision here corresponds to this here, or vice versa. So this is what you want to look at. It's just not true that you can't use this to follow progression. You can watch precisely what's happening to this. That region right there, let's blow it up, right? So we're going to watch what's happening over time. Is what we're doing in the clinic at the moment with data. Is watching how this is changing over time. And you can see in some eyes it would be preserved for a couple of years, and other eyes you can see it marching towards fixation here, which would be right there. Here's another example. 54 microns global, -22. On this plot it would be about there. It's got two regions of preserved vision according to the 24-2 here, by the red arrow, which would correspond to that, and here with the green arrow, which corresponds to that. Let's blow this up. There is the region that corresponds to the red arrow on the field. There is the region that corresponds to the green arrow. Here's the 10-2. There's your region of preserved vision here, right? And there it is there, and there it is here. And again, we can blow it up. You want to watch this closely to see how this is changing. And again, this point's right smack in the middle of the region that's not supposed to be useful. Okay, so without going into details of these 49 eyes, all but only 5 of them would be hard to follow for a variety of reasons. Okay, so challenge number 3, you want to inspect, because of challenge number 3, you want to inspect the scan image. You can use OCT for eyes with advanced glaucoma or high myopia as well. All right, so the final point I want to make here is that it's also useful. Other reason for looking at scan images, it gives you a better understanding of the nature of damage. And I think once we get used to looking at these images, we're going to rethink how we understand and categorize glaucomatous damage. Okay. So this is summarized in a recent Progress in Retinal Eye Research paper. So let's step back and ask, how are defects categorized? Well, here's one ambitious scheme by Keltner, Johnson, and colleagues that was used for the OATS trial. And I've redone this figure of theirs so that these are all upper visual field examples. So, this is a nasal step, this is paracentral defect, partial arcuate, arcuate, altitudinal, right? So let's just, these regions, all upper field defects. Okay, what can we learn from OCT about patterns of damage? How do they relate to what we're seeing here? Well, here's our model for the temporal half of the disc. This is the region of the field and the region of the retina associated with the temporal half of the disc. And superimposed is a map relating the location of the 24-2 points for an average eye. So how is it related to, let's relate this to our model here. So all of these defects here are falling in this region here. That is, they're associated with this region here. This is retina view. Let's flip it into field view and superimpose it. So that's what the model would look like for each of these. So in each case here, right, the temporal half of the disc is associated with the region in blue here. First of all, I should have mentioned this is 30-2, so you want to drop the outer ring of points to correspond with this, which is a 24-2. The 30-2 would come out here someplace. Okay, in any case, the model here also fits this here. These points here would be around on the nasal side. All right, so these upper visual field defects are all of these here within the blue region are largely due to damage in a 45 to 90 degree wide region. In fact, they're probably less than 90 degrees. Most of these are damage in this region right here and right here. That's the macular vulnerability zone, so damage includes the macula. All right, so based upon OCT scans, we should expect a wide range of patterns of visual field loss. So again, let's just look at this region here that's associated with these defects. So here's one eye. Let's take this and blow it up. Here are 4 other eyes. So what do we expect if we just look at the OCT? How can local damage vary? Well, it can vary by width. So this damage here is pretty wide. The region of damage, pretty wide, probably more narrow. The location can vary of the deepest part. So right here, this is the deepest part here. The deepest part here is more towards the inferior pole, and the deepest part here is even further. Depth, so these are very deep. This is less deep. And then homogeneity I mentioned before. If you look close, you can often see local variations. All right, so given that variation, we should expect a wide variety of visual field defects. In fact, we should expect an infinite variety of visual field defects. And that's what we get. So here are the visual field defects shown as probability plots for these 5 eyes. There's our model, and you can see the points falling within the model and the various variations in the visual field defects. Again, we're talking about damage in probably just this region right about here. Relatively small region. Okay, so just to repeat, the point we're making is you want to look at and carefully inspect the scan image. And if you skipped to the module, where can I find this on my machine, I will present more information about that. But first, I want to leave you with a final thought. And this will also be part of a standalone mini lecture. And the thought is the following. Glaucoma specialists are not making optimal use of this incredible technology. They should be looking at scan images. And to bring this home, I want to compare this OCT image here of my eye to the OCT image of my brain here. There's much better resolution in the OCT of my eye than the MRI of my brain by about an order of 2 magnitudes, or 2 orders of magnitude that is, or about a factor of 100. To bring that home, what I'm showing here is the 6 millimeter section that would be the same size as this scan. So if you blew this up, you would see nothing. But you have all this detail in that same area. Now, how are we making use of that detail? Well, to make the contrast to the MRI, or comparison to the MRI, let's assume this is a tumor in my brain. As a matter of fact, it's not. It's benign fat that's in my forks. But anyway, let's assume it wasn't benign structure, but it was real. How would we want the radiologist, or how does the radiologist go about analyzing this? Do they take this image and put it into a computer program that then segments the brain and then determines the regions that are hyperreflective, and that then turns it into a probability plot so you know where it's significantly different? And then maybe, would you want them to chop this up into sections and then average those sections? Well, this image, this pizza pie plot from the OCT, that's what we're doing with these images here, or in this case, circumpapillary images, right? And then we look at global thickness often. Would you want your brain analyzed here based on global thickness changes as opposed to changes locally? Of course not. Instead, what the radiologist does is blow this up and look carefully at the margins to see if it's getting larger over time, right? That's what we just suggested one should be doing with the OCT circle scans. Same thing when you want to, we can make the same kind of comparison to radiology and neurology and neurosurgery in terms of comparing structure and function. So the neurologist faced with this problem doesn't take an average sensitivity of my whole body and then asks if it's changing. The neurologist notices that in this case, it appears to be in postcentral gyrus, somatosensory region, pressing on the thumb. So he or she will examine the thumb or the hand to see if there's somatosensory changes. Well, and compare structure and function. That's what we're suggesting we should be doing with the OCT as well. So again, an incredible technology. We're not making optimal use. And here are our suggestions, and they include looking carefully at a scan image. Thank you.